So here we have an additional example from 14.7 part 2, where we're looking at finding absolute extrema. Here we have a rectangular aquarium with a given volume V, made of slate, and the sides are made of glass. The base is slate, the sides are glass. Slate costs 5 times as much as the glass. Find the dimensions that minimize the cost. Okay, so lot in there. Let me just get the big picture. We're trying to minimize the cost. And our constraint here, do you see what it is? Our constraint is that the volume is fixed. So let me just call it V. It's a fixed given volume. So we need to find an equation for the cost. So I'll do that over here. So we want to find an equation for the cost, a function. All right, well, let me just call the dimensions of this box. Let's let z be the vertical, and we'll go y here and x here. And what else do we know? The slate, the bottom, costs 5 times as much as the sides. So let's let C be the cost per unit area of the glass. Then what does it say about the slate? It's 5 times for the slate. So the cost is going to be the cost per unit area times the area, right? So for the base, that base, the area there is x times y, and it cost $5C per unit area there. So it's going to be 5C times xy. That is the cost of the base. The front is made out of glass, so it's going to be the area is x times z. The cost per unit area is this constant times that, so c times xz. That's the front. So c times x times z, that's the cost of the front. The back will be the same. This left side over here, this is z. So the area is y times z. Multiply it by the cost. That's how much that left side costs. And we have the right side as well, so we multiply it by 2. So this is our cost, let me just emphasize, as a function of 3 variables. That c is a constant. I could factor that out if I want to. So I just get 5xy plus 2xz plus 2yz. So that's what we are trying to minimize. That's what we're trying to minimize, that, subject to the constraint that the volume equals V. Well, the volume of that box would be x, y, z. So in this section, we are incorporating the constraint into the function that we want to optimize. So, for instance, if I solve for z, z equals v over xy. Remember, v is a constant here. So if I incorporate that here, then I'm going to get my cost function now as a function of x and y only, because we've incorporated the z, is a constant times 2xy, whoops, that's a 5xy, plus 2xz, z is v over xy, plus 2yz. Z is v over x, y. So once again, I have just substituted in for the z. And so my cost function is this constant times 5xy plus 2v over y plus 2v over x. Okay, so that's the function that we're going to deal with here. Okay, so we find critical points. Really helpful if you have a couple words here and there. It makes it easier to follow. So critical points are when the partial with respect to x and the partial with respect to y are both 0. So go ahead and compute those partials. Go ahead and pause the video and compute those. Okay, and so solving this system, let me bring over here y would be 2v over 5x squared. And let me just write this one here, divide by c. Then I get 5x minus 2v over y squared equals 0. So there's my system. I'm going to substitute the y in for here. So when I do that substitution, I get 5x minus 2v divided by y squared, where y is 2v over 5x squared. Minus 2v over 4v squared over 25x to the fourth. And so that is 5x minus 50v x to the fourth over 4v squared. Which leads me to factoring out the x, I also divided out one of the v's. Actually, this should leave me with a v here. So either x equals 0, which doesn't make sense here because we would not have a box, or 50x cubed over 4v equals 5. 50 x cubed equals 20v. So x cubed equals 2/5 v. Okay. Find the corresponding y that goes with it right here. So y equals 2v over 5x squared. And so we're putting this in here. And so that's 2/5 v, 2/5 v to the 1/3. And so that's going to be 2v over 5. And that is squared, so that's to the 2/3. So that's 2/3 v to the 2/3. So that leaves me with a v to the 1/3 on top. We've got a 2 here. This is a 5 here. So 5 to the 2/3 and 5 is 5 to the 1/3. And here I will get a v to the 2/3. I already took care of the v. 2 to the 2/3 and 2 would leave me with a 2 to the 1/3. So 2v over 5 to the 1/3. So that's our critical point. X equals 2/5 v to the 1/3, and actually so does y. Now, that's the only critical point we got. We need to validate, though, whether or not that leads to an absolute minimum. And this is one of those that the way you're going to figure that out is to argue physically. There would be a box of minimum surface area here, not maximum, because you could let these sides go approach 0 and then the height would approach infinity, some such thing like that. So we don't have a box of maximum surface area, but we do have a box of minimum surface area. So I would expect something like this here, since there must be a box of, well, it's not minimum surface area, actually we want its minimum cost. So minimum cost, and this is the only possibility, then this critical point yields the minimum cost. Okay, so that's the validation I tell you I'm always looking for. And then the final part is we got to make sure and answer the question. Sometimes the question would be, how big should we make the box? Sometimes it's, how much is it going to cost? So we have to go back up and look at the question. The question was, find the dimensions of the aquarium. Find the dimensions that minimize the cost. So the dimensions are here. The dimensions are the length and the width need to be the third root of 2/5 v, and then the height is z, and z was volume over xy. Z equals the volume over x times y. And if we do that, we're going to end up getting here, which I suppose we could write as 5/2 to the 2/3 times v to the 1/3. So those are the dimensions. Hope that helps.